All right, guys. So I think this part is clear. The A part you can do by yourself. The B part also along a similar line. I will just write the equations for the B part because seems to be there are too many objects, right? You just go and write the equations and then solving will just write directly the shortcut. Fine. For the B1. So therefore, for the B case, over here you have the mass of M2. This is the pulley over here. This is another pulley over here. This is the other mass over here. Fine. So this is nothing but M2G. The tension will differ because in order for the pulley to rotate, there must be a net torque, there must be difference in the tension values. Otherwise, it's not a smooth pulley. So far in Newton's law, you have studied that it is a what kind of a pulley? It's a smooth pulley, right? Here, no more. Fine. Rough pulley it is. Only then alpha is there. Only then difference in the torque is there. Fine. So on this pulley, it will be pointing this way, the tension force. And over here, it will point this way. The value of tension will be different. And over here, mass is how much mass? Was it M2? Yeah. You get M2G, and here there'll be T3. Fine. This one had a moment of inertia of I1, yes, I1 and R1 are the data for this one. This one has I2 and R2. Okay. There'll be 4 equations and 1 constraint. Okay. 4 Newton's law for these objects. 1 constraint for the relating the alpha values. Or are the 2 constraints? Okay, let's write. So therefore, over here on this one, what can we write? Taking the M2 to be heavier. This is the direction of acceleration. Everywhere you'll be having the same magnitude of acceleration. Oh my God. Which is M1 here? The right one is M2. Okay. So change this one. Fine. So this one over here is M1. This is M2. M2 is heavier. This is the acceleration direction of M2. M1 will be upwards, therefore it is lighter. Goes up. Let's write the Newton law over here itself, right? On M1. What is that on M1? T1 minus forces are also there. Change those forces. Fine. T1 minus M1G is M1 equation number 1. On M2. M2G minus T3 is M2 into A, equation number 2. Torque equation on this one. On the pulley, the net torque. Now, if that is going upward, alpha must be to the right side this way. That is the clockwise sense. And since the radius is different for the 2 pulleys, let's write it alpha 1. So since the alpha is that way, the T2 torque must be greater than the T1 torque. The R perpendicular will be this R. So we can write T2R minus T1R is I1 into alpha 1, equation number 3. Similarly, on the other pulley, what can we write over here? Acceleration, angular acceleration will be such that it will be in this way. Because that M3 is moving down, right? So the right pulley must rotate this way, clockwise. And it's alpha, let's write a different alpha, alpha 2. So it becomes how much? This torque due to the tension T3 minus the torque due to T2 is equal to moment of inertia I2 multiplied by alpha 2. This becomes equation number 4. And what's the constraint over here? Now, over here, the accelerations must match. And over here also, the accelerations must match. So for the constraint, we will have to write that the tangential acceleration of the pulley which is on the left pulley, we took the radius as R2. So R2 alpha 1 is AT must be equal to A. And on the right pulley, oh, I'm sorry, extremely sorry, guys. Actually, R1 radius. Okay. And on the right pulley, what is the other constraint? Again, tangential acceleration is R2 alpha 2. It must match with A. Fine. So you get how many equations? 4, 5, 6 equations. We'll solve 6 equations. Not me, not us. Just directly write. That's why these expressions are can directly write the value of this acceleration as net pulling force divided by the total equivalent mass. Fine. Fine. This part is clear. Moving on to the next one. What is the next problem? Let's go. This is done. This is done. What about the C case? C case in the same way you can do. So over here you have this pulley, and this is the mass of M. Moment of inertia is I. Radius is R. Directly you can write the acceleration. Net pulling force divided by the total equivalent mass. That's all. Newton's law you can write. This one will be your mg. This one will be your t. Over here there will be a t. One torque equation, one Newton's law equation, one constraint. 3 unknowns, t, a, and alpha. And therefore 3 equations for these 3 unknowns. Fine. Fine. Let's just write that on M. What is the equation? mg minus t is equal to ma. Equation number 1. And what about on the pulley? Again, you can write tr is I alpha. Equation number 2. And the constraint, what is that? What is that? Let me just take a coffee break over here. Give me a minute. You guys can have some, I don't know, milk or Horlicks or Complan that you, I don't know what. I'm just joking. Constraint. So what is that? So you write A as equal to R alpha. Fine, this becomes your, solving them, you get the answer. Moving on to the fourth one. What is the fourth one? The D. So this one is different. You will do the greater detail analysis for this one. So this particular rod over here, which has a mass of how much M, has a length of L, it's released from rest, right? And what are you asked to find? Find the angular acceleration. When do you want to find out? Let's say that you want to find out just after the release. And just after what? Release. You have to let go of all negativity, gentlemen. Be positive, stressless. Stressless is the best. Okay, coming back. So the forces acting on this one are, as soon as you let go, there will be some force of mg. And over here, there will be a reactionary force. Otherwise, the plank has to simply fall down. Who's preventing the falling of the plank? Who's preventing that? Someone, right? So that force is the reactionary force. You can call it an RB vertical. Now, initially the RH, the horizontal force will be 0. But you have to write it into 2 independent components, RV and RH. Yeah, they will exist. We'll come to that later. But for now, RV and RH, you just write. So what's the way to find out torque equation? This becomes a fundamental doubt for many of us about which point we're supposed to take the torque. This one is fine because the entire rod is in pure rotation about the hinge. In this way, the rod, every particle of the rod is going to rotate this way, right? It's going to swing. So it becomes convenient for us to imagine that the hinge point is the point about which we'll take the torque. So let's do that. I about the hinge into the alpha. Fine. Now, what is the torque of RV and RH about the hinge? 0, because they pass through that point. 0 it is. What about the torque due to mg? Mg, this is a line of action. Action. Cut. Action. This is the line of mg, and this distance is L by 2. And what is the sense of the torque? This way. And we'll take the alpha also this way. So you write plus mg into r perpendicular, which is L by 2, equals I. What is the moment of inertia of a rod about one hinge? We did discuss it, ml square by 3 alpha. That's all, gentlemen. Just after release, this becomes alpha as shifting and substituting. I get P by 2g by L. Fine. We won't stop there. Just hold on. Just give me a minute. Now, suppose you are also asked, this is only the A part of the question. There's more to this. Find the hinge reactionary forces. Just after release. Find the hinge reaction after what? After the release. Release. Fine. So what do you get over here? Well, for finding the hinge reaction, we need to use the Newton's law. So again, what are the forces acting? This one and this one. And if you recall, we do not know right now. Just put over here RH, right? Because it's not a string, right? Such that there will be always upward tension. No, it's a rod, hinge is there. Let's look at the center of the mass. Now, does the center of the mass just after release have any omega value, angular velocity? 0, right? So therefore, since the center of the mass is going to move in a circular path, what is the centripetal acceleration? If we take this distance as small r, which is L by 2, centripetal acceleration is r omega square with respect to the center of rotation. This is the acceleration, right? So this one will be 0 initially. Okay, so AC is gone. Then which other acceleration is the tangential? The tangential acceleration of the center of the mass is AT. But AT is nothing but equal to R alpha. Correct? This we know from circular motion. And R over here is L by 2. And now we are ready to write the Newton's law. Along the horizontal direction. Along the horizontal, F net is equal to M into AC. AC is 0. Therefore, RH is the only force along horizontal. It goes. RH is 0. Now let's go for the vertical. Along the vertical direction, what is the net force? F net equal to MA, which means let's take the downward direction as positive because A is downward. The AT value, the R alpha value. So mg minus RV is M into A, AT, M into R alpha, M into L by 2 alpha that you found out just now. Fine. On the left hand side, mg minus RV. So how much is the value of RV that you get? mg minus 3 by 4 mg, which is 1 by 4 mg. This is your RV. Important. Conceptually very important this one is. So therefore, since RH is 0, the hinge reaction is only RV. If there was a hinge reaction, then you'll write the reaction as root of RH square. Hinge reaction vertical component square plus the hinge reaction horizontal. Fine. Okay. So this was on this one. Let's take this question further. The same D part, A, B, and C. Fine. Suppose this one is released over here. From rest. So as it moves, let's say that now it is making an angle of uh, theta this way. Fine. At this instant, what is the value of angular acceleration? Mass is m, length is l. Fine. Rest, it is released. Find the angular acceleration at this instant. What do you do? There's no difference, same it is. Torque about the hinge equal to I alpha. Torque about the hinge will be due to all the forces. In this case, due to the mg. The mg is acting which way? Downwards, this way. And what is the perpendicular distance of mg from the hinge? It's this distance. It's not L by 2, like in the previous one. This is the distance which is L by 2. So if you observe, L by 2 cos theta is the distance. Fine. So now we simply write that this torque for the hinge is I alpha and mg L by 2 cos theta is about the hinge. The I value of the rod is how much? ml square by 3 into alpha. Cancelling the terms, you get alpha as 3 by 2 g by L. This is done. Fine. All right. So this is okay.